Alright, welcome back to part 2 of my video on the concepts covered in your summer work for AP Physics. We're going to focus our time in this video on the physics review, which is the second packet. I'm going to skip the majority of the content that's covered in chapters 2 through 7 because that's the majority of what we spent our year on last year, from 1 and 2D kinematics and then 1 and 2D dynamics. So you're essentially doing known unknown tables, and remember, in one dimension you have your knowns on the left, your unknowns on the right. In 2 dimensions, though, we constructed the table where you have all your x known unknowns on the left, all your y known unknowns on the right. And then doing free body diagrams, fun equals ma, system of particles. You guys should be able to at least work your way through those types of problems. If anybody needs additional help, let me know through Remind or leave me a comment. And what I can do is then we could set up a time to have a review session together at the school, just as long as we're able to get into the school. I know at the beginning of August is when they're going to be really focused on taking everything out of the classrooms and getting the school ready to go. So we might not be able to get into the building. But if we can meet and that's something that you guys are interested in, just let me know. But we're going to start in chapter 8. And one of the hints that I had given at the top there is about Kepler's law. And there's 3 laws that Kepler provided us about how planets moved. Kepler came before the time of Newton. We actually went over Kepler's third law, and what you might remember it as is when we combined UCM, uniform circular motion, with universal law of gravitation. And so we started off with saying that the centripetal force for any satellite, which is an object moving around a bigger object, like the Earth going around the Sun, or an artificial satellite going around the Earth, or the Moon going around the Earth, that the centripetal force, the inward seeking force pulling the object towards the center, is gravity. Now, the centripetal force is the mass of the object that's in orbit times its tangential speed squared divided by the radius of its orbit. And that equals Newton's universal law of gravitation, which is big G, is Newton's gravitational constant, times the mass of the object that the satellite's going around, times the mass of the satellite, divided by the distance between the big mass and the small mass squared. Now, I could call distance d, but d equals r when you have if we were to say the Sun and the Earth going around the Sun, which is really what Kepler was intending on with his expression, that the distance d that we're talking about here is from the center of the Earth to the center of the Sun. Now, at this scale, both the Sun and the Earth would appear to be dots, to see the whole orbit of the Earth going around the Sun. And so the size of the Earth and the Sun really is irrelevant anyway, and we could just get rid of the Earth and the Sun completely and just look at the circle and say, okay, this distance here is nothing more than the radius of this circle. So that's why I can instead of using distance squared under here, it is for this case that I can say that this is r squared. That would not be true if we were talking about, let's say, two suns, two stars that were orbiting each other. So if that's the case, let's say they were of equal mass. In this example, what they would be orbiting around would be the center of mass. And so it would turn out that the radius of their motion would be d over 2. It would have to be half of that distance. And so anywhere you would need to use radius r, you could set that equal to d over 2. So this is specifically, in this expression, the radius of the orbit. This is specifically the distance between the two masses. And in the example of the Earth going around the Sun, this is true. But in this system, r equals d over 2. And so that's what I would have to plug in here. So that's where a lot of students will generally make mistakes when we get to doing more advanced astrophysics later on in the year. If these two suns were of different masses, then it gets even more complicated, because this center of mass shifts. If this was a big star and this was a small star, the center of mass would shift towards the big star, and now this star would orbit not like this, but this would be the radius of that star, and so it would go sort of like that. Well, let me try to do it in 3D. Something like that. But this star, its radius would be this. And so it would orbit more like that. And it's a pretty complicated ordeal. They would always stay on opposite sides of each other as if they were attached by some bar. So that would mean that this small star would have to move around much faster, because in the same period of time they make one revolution around their center of mass. So for instance, this star would be here the same time that this star would be here, and so the small star would have to whip around the center of mass a lot faster. So this is all stuff that we'll be talking about later, and completely just above the scope of what you have to do for the summer work. I just thought that would be interesting for you to know. But to go back to deriving Kepler's third law, here we're going to cancel out a couple of things. The mass of the satellite in this case doesn't matter. Again, would not be true in this system. It's the fact that the mass of the object that the satellite's orbiting around is so much bigger than this mass that the mass of the little object goes away. And we lose an r on both sides. So what I'm left with here is v squared is equal to gm over r. But if we want to get the period into this expression, because that's what Kepler's law relates, is the period of revolution of these satellites to their distance from the center of their orbit. The way we can bring that, the period is 2 pi r over big T. And I can substitute in this expression in for v, but I could also, before I do that, just say, okay, let's substitute in what v squared would be. So I'm just anticipating that that's what I'm going to be doing, is I'm going to have to square everything anyway. So I get 4 pi squared r squared over t squared. And so now that I can substitute in here. Making sure I'm not losing any terms along the way. And now I just want to get the t on top, and I'll get t by itself, and then everything else I'm going to put onto the other side. So I'm going to bring t upstairs. It's t squared. And then in order to get t squared by itself, I have to multiply both sides by r, so I get an r cubed. And then you have an assortment of constants in this formula. So you have the 4 pi squared, and then we're going to have to divide both sides by g times m. So kind of going back, reflecting back on what we talked about with graphs and constants of proportionality and meanings of gradients and things like that. If I were to graph t squared with respect to r cubed, because what I have in parentheses there is a constant, this should produce a straight line, and the slope would be this quantity here. Now, the slope, this is some number, some obscure number, depending on the system that you're talking about. If you're talking about the Earth going around the Sun, then you would plug in Newton's constant, and you'd have to plug in the mass of the Sun. You'd be using standard units of Newton's constant is in units of newtons times meter squared over kilogram squared, and the mass of the Sun would be in units of kilograms, and so you get some obscure value with these weird units. If you were talking about a satellite going around the Earth, then you would still use the same value for big G, but then you would use the mass of the Earth because that's the thing that the satellite is going around. So those values change depending on the system. What doesn't change is the relationship, which is that t squared is proportional to r cubed. So depending on what the big mass that you're going around is, that's going to determine the value of your slope. But this relationship comes directly from setting the centripetal force equal to just gravity, and that's true for any orbit in our universe. But what we did in class was, there's a coincidence, a cosmic coincidence, that we can set these two things equal to each other, which implies that we are saying the constant of proportionality, that 4 pi squared over gm, is just equal to 1, and 1 with appropriate units, so that way when you square the t term and you cube the r term, that what you're left with cancels everything out. So it's 1 with a unit, with units, the appropriate units around it. So, but we happen to get the value 1 for that constant, given that you use units of years for the period, and this obscure unit of an AU, which is an astronomical unit. That's the average distance from the Earth to the Sun. We use that for units of R. Now, that's if you want to actually do very quick calculations. So using these units, I can set those two things equal to each other. If I knew what the value of the distance of a planet away from the Sun was in astronomical units, I can quickly, very easily get the value of the period in years, which in the case of the planets going around in our solar system, it's a very useful, quick type of calculation that we could benefit from using. I could get the same results by using this more elaborate formula, where I'd now go back to standard units. I'd have R would be in meters, so I'd have to know the distance from the Sun to the planet that I'm talking about in meters. I need to know the mass of the Sun. I need to know big G. I have to use these constants. And then when it's all said and done and I calculate big T, I get the period in seconds, which could be some obscurely large number because it takes, for any planet that's beyond the Earth, it's going to take years to go around the Sun, so that's many, many seconds. So, but you can then convert from seconds into years and find out that it's exactly the same answer, or at least very close to it, because this isn't exactly one, but it's close enough. So you get roughly about the same answer as you would doing it with this short expression. But if you're dealing with ratios, then you could use any units for time and distance that you want, because again, this relationship holds true. If you're not concerned, if you're dealing with objects in the same system they would all be points along this line, right? They all obey this particular relationship, then it doesn't really matter what units you use. And so I want to give you finally now one example of that. Let's look at number 1 in chapter 8. The distance between the Earth and the Sun is often expressed as 1 AU. Using this unit, find the distance between the Sun and Mars, which has a period of approximately 686 Earth days. So first off, you cannot plug in directly 868 days in for big T, square it, cube root it to find R, and expect to get an answer in astronomical units. That's not how this formula works. If you could convert 686 Earth days into years and then do it, that would be okay. All right, you can convert first to years, days to years, and then solve for R. That would be appropriate. But the other way you can do it is by saying that, let's just say, because of this relationship holds true, that means that the period squared of the Earth is proportional to R cubed of the Earth, and it must also hold true that the period squared of Mars is proportional to the distance of Mars cubed. When you have two expressions like this, what you're able to do is divide them. Because they have both the same constant of proportionality, because they're part of the same system, the constants drop out. So the other way we can you can see that is if I replace alpha with an equal sign and then place our constant of proportionalities. Now we know k is related. It is this 4 pi squared over gm, but whatever that number is depends on the units that were used to calculate that value. So it could be in kilograms, it could be in meters, it could be in seconds, it could be in years, astronomical units, it could be whatever. But by dividing these two expressions, what we're doing is eliminating the need for the constant, because let's see what happens. We get T Earth squared over T Mars squared. That equals, and you see here that the k divided by k cancel out, and you're left with r cubed of the Earth divided by r cubed of Mars. Now, as long as the r's have the same units and the t's have the same units, then you can use whatever units you want now. So, and the way the other way you can see that is this could be rewritten as a ratio of the periods, the whole thing squared, and that can equal the ratio of the distances, the whole thing cubed. So if the top is in seconds, the bottom better be in seconds, because they got to cancel out, because the ratio on the left has to equal 1. So that way, if I were solving for, let's say, one of these r's, that this thing can't have units, because this r is going to be in meters, so then meters times 1 is meters, and so I'm left with the same unit as I started with. So in this case, I'm looking for the distance to Mars. So I'm solving for Rm. So I'm going to modify this a little bit. I want to keep these guys split up. Because I want to solve for Rm cubed. So I'm going to bring Rm cubed up top. And so I need to divide both sides by this whole thing. So that's the same as multiplying by the reciprocal. So check to make sure you understand this step and that I didn't make a mistake. Alright, so I divided both sides by TE over TM squared, but that's the same as multiplying by the reciprocal, so it's multiplying TM times divided by TE squared. And the last thing you do is cube root it. I'll wait a moment to do that. Now you just plug in whatever values you have. Again, I know R is in astronomical units, so this RE is 1, so I cube it and I get 1 AU cubed. When I cube root it later to solve for Rm, I'm back to having astronomical units. So that's the way you want it, and that'll work just as long as the units that are in here cancel out. So I know that the TM that was given, the period of Mars going around the Sun, is 686 Earth days. So if I'm talking about days, then I can't say 1 year for the Earth. I have to say 365 and a quarter days if I want to be accurate there. So RM cubed equals 686 days divided by 365 days. I'm leaving the quarter out because it's just 3 sig figs anyway. And then this was 1 AU cubed. The days cancel, and when I take the cube root of both sides, I'm going to get what's left over, which is going to be RM equals, and it's going to be whatever this is, 686 divided by 365 cube rooted. The other way you can express that is as a fractional exponent. Cube root is the same as something raised to the third power, times 1 AU, which I don't have to write the 1. So this next step is just simplifying, which I got 1.5 AU. And so that's the extent of what you should be able to do with Kepler's law. Now in Chapter 9, that is dealing with a concept that we've never talked about. So let me give you a little bit of background information. I do give you some important equations, and for the time being, you just accept them as fact, and when we get to this unit, we'll understand more about why these equations are what they are, or why these concepts are true. But Chapter 9 deals with momentum, and momentum is a quantity that we often use in physics. It's given the symbol P, which I never quite understood. And the way it's defined is the product of mass times velocity. Mass is a scalar, so it doesn't depend on direction, but velocity is a vector. So whatever direction velocity is in, that is the direction of this quantity momentum. So a simple example is, let's say you have a mass of 1 kilogram, and let me go back. Let's just be a little bit more interesting. 2 kilograms. And it has a speed, or velocity in this case, of 1 meter per second squared. 1 meter per second. Then what is its momentum? Its momentum would be 2 kilograms times 1 meter per second, and so you get 2, and you're left with kilogram meter per second. And there's really, that's typically the units that are used. Although, if you recall, a Newton is a kilogram meter per second squared. So I could swap out one of these seconds and bring that over here and get a Newton second, and that would be the same as a kilogram meter per second. So that means that another acceptable unit for this quantity would be 2 Newton seconds. But typically, this is the quantity, the unit that we normally stick with, depending on the circumstance of the type of problem that we're doing. But you can also then represent momentum as a vector. And the rule is that the momentum vector is in the same direction as the velocity vector. So it is a vector that is 2 units to the right, just like velocity was 1 unit to the right. So the momentum is essentially then going to look something like that. So the mass in this equation can't change the direction of the way that the way that the arrow is going to point. If you know what the direction of the velocity was, then you automatically know the direction of the momentum. The mass can only make the arrow bigger or smaller. If I multiply by a value less than 1, but still greater than 0, because you can't have a negative mass, if I multiply by a half, then it makes the velocity vector look half as big when you get the when you make the momentum vector. If I multiply by 10, then the velocity vector, or the momentum vector, will look 10 times bigger than your velocity vector. So it can change the size of your vector, but it cannot change the direction. And that goes in 2 or 3-dimensional space. So if an object in 3-dimensional space is moving in this direction, which could be sort of out of the board here, then the momentum vector, depending on the mass, let's say the mass was greater than 1, will look like that. Right, it would be in the same direction. The other thing you need to know to do these problems is something called impulse. Impulse is defined as the change in momentum. It's also given the symbol J, which is also a vector. And so impulse is just the change in momentum. Now there's an interesting relationship here, though, that we'll get into a lot more detail later on. If you read Isaac Newton's work, when he first writes down his laws of motion, you'd be surprised to know that what we've come to say his second law to be, which was is our fun equals ma, is not the way he expresses it in his book. He doesn't define acceleration. He defines a quantity that's changing with time. And so, since acceleration in a discrete sense is the change in velocity over time, we can replace acceleration with delta v over delta t. And we know, based on this definition up here, that mv is momentum. So m times delta v, as long as the mass of the object isn't changing, so something is changing here. If the velocity is changing, it's speeding up, it's slowing down, it's changing direction, but we're assuming that the mass isn't changing. If the mass isn't changing, then m times delta v is just the change in the momentum. So we could rewrite fun equals ma as F equals the change in momentum over the change in time. And that's actually how Newton describes his second law in his book. But then you could multiply both sides by delta t, and you get it into this form, that delta p equals force times delta t. According to this statement, delta p is what we have now defined as impulse. We can also write impulse as force times time. So the impulse that an object experiences is a force over a given time period. So if you're kicking a football, the impulse on the football is going to be the force that the ball experiences while your foot is in contact with the ball over the period of time that those two objects, the ball and your foot, are in contact with each other. Whatever that impulse is, that is going to cause a change in the momentum. Now, assuming that your foot and the ball don't change in mass, then what does a change in momentum say about what will happen to the ball? If there's a positive impulse, then you're going to get a positive change in momentum. And if the mass of the ball doesn't change, that means you're going to get a positive increase in velocity. So by kicking the ball, you get the ball to go fast. And it happens quickly. So, I mean, in the span of whatever this delta t is, whatever the time that your foot is in contact with the ball, that's the time that your momentum, the ball's momentum, is changing. And so in that time period, it could be a fraction of a second, it picks up quite a bit of speed. And then that's the point in time that the ball would then go into like projectile motion, and we could use all those techniques to figure out where the ball will land and all that stuff. But if you want to know what effect kicking the ball will have, you need to understand the concept of impulse. When you're dealing with more than one object, then the other thing that you're going to be concerned about is a concept called conservation of momentum. In most practical applications of physics today, physicists often concern themselves more with quantities that they know are conserved. All right? So momentum is one of those quantities that is always conserved between two objects. We'll get more into detail with that later. This past year we talked about the quantity that we called energy. Energy is also a conserved quantity in specific circumstances. Specifically speaking, energy is conserved when there are only conservative forces acting on your system. But momentum is always conserved. And so that means that whatever momentum is before an interaction, after the interaction, the momentum has to be identical. If there's no interactions, you have just one object, one mass, one velocity, then the momentum should be the same, non-stop. That's just Newton's first law. Objects in motion stay in motion. If they experience a force, that's an interaction. That means there's more than one object in this system now. Two objects collide. A planet uses its gravity to pull on an object. That means that the momentum of one object might be affected by the other object. But what this conservation law states is that the total momentum of the system that we're talking about is always going to be the same. So the way we calculate a total momentum is using vectors. So the vector sum of all the momenta before an interaction has to be the same as the total vector sum of momentum after the collisions or interactions. So the techniques that we use to solve those types of problems will depend on how many dimensions we're going to be dealing with. So one dimension, we don't really have to talk too much about vectors. But in 2 dimensions, you already have to start to worry about components. And so let's take a look at one of those examples in Chapter 9. Number 1 says a ball with a mass of 12 grams moving at positive 15 meters per second collides with a second ball of mass 36 grams moving at 5 meters per second positive direction. After the collision, the 12 gram ball is now moving at positive 6. What's the change in momentum of the 36 gram ball? So we have 2 objects, and the way we're going to denote things here is we'll define some mass to be m1 and some mass to be m2. They get corresponding velocities v1 and v2. That's before the collision. After the collision, we know that the objects maintain the same masses. So, they don't break off into pieces, they don't merge together. So we after the collision, we still have m1 and m2. But their velocities might be different. And so now to denote the change in each velocity, for the first object, its velocity after the collision will be v1 with this little prime symbol up at the top right. And similarly with the second object, it's v2 prime. So what this expression translates into for a system of 2 particles like this in 1 dimension is m1 v1, that's the momentum of the first object, plus m2 v2, which is the momentum of the second object. That has to equal the total momentum after the collision. So that's the total momentum before, that's going to be the total momentum after. So the total momentum after can be expressed as m1 v1 prime plus m2 v2 prime. If after the collision v1 prime, for instance, is exactly the same, then v2 prime has to be exactly the same. But if v1 is different after the collision, then v2 is going to be different after the collision. So we're told that, and you could convert the grams into kilograms or leave them leave it in grams as long as it's consistent. I'm just going to leave them in grams for right now. So 12 grams, and it's moving at 15 meters per second, and the second mass, 36 grams, moving at 5 meters per second. That has to equal 12 grams times 6 meters per second plus 36 grams, and you don't know what the speed is of the 36 gram object after the collision is. So I have nothing to plug in there. But since it's the only thing I don't have, I can solve for it. And so you can use these values to determine what V2 prime is. But that's not the answer to the question. The answer is, what's the change in momentum of object 2, or 36 gram mass. So that's the momentum after. So it's P2 prime minus P2, which is M2 V2 prime minus M2 V2, and I could factor out M2. So that's going to be 36 grams times V2 prime, which you'll need to figure out, minus 5 meters per second. So once you figure this out and plug that in here, this will be your answer. Now, if I skip 2 and go to number 3, now we have a situation where we're dealing with angles. And now this conservation equation has to be considered more in terms of vectors a little bit more carefully. So in this case, you have two objects. The first one has a mass of 5 kilograms moving at 4 meters per second, and it collides with an object that is at rest. So it still holds that P, the total momentum of the system, which is of these two particles before, has to equal the total momentum of the system of these two particles after. So we have two objects. They have the same mass, so there's no need to say distinguish between M1 and M2. Let's just call them M because it's going to be the same thing. We know what V1 is. That's the 4 meters per second. And we're assuming that it's moving to the right. And that V2 is 0. Now, given that that one of the spheres moves off at a 60-degree angle, that's enough for us to figure out not only what the speeds are after the collision, but then also what the direction is of the second sphere will have to be. So if we write our expression here, we're going to say that M, which is M1, V1, and that's a vector, that equals or the plus, let me do this in full steps here, mv2, that equals mv1 prime plus mv2 prime. Now notice the first thing that happens here is that because the masses are all the same, all the masses disappear. The other thing that disappears is V2, the initial, because this is equal to 0. So that goes away. So what you have here is V1 equals V1 prime plus V2 prime. In a picture form, we already know that V1 has to look like that. So V1 prime plus V2 prime has to also look like that. Those are supposed to be the same length arrows. But what we know to start is that after the collision, the first sphere moves off at a 60-degree angle. So after the collision, you have one of the objects, this is V1 prime, moves off at a 60-degree angle. Well, how can we compensate for that when we know that together V1 prime plus V2 prime have to add up to give us nothing more than a vector in the off to the right. So now the big hint that I'm going to give you here, which does need some explaining, but I'm going to hold off on that till again we get to this unit. But when you have two objects that are the same mass, if one starts off at rest and the other one comes in at along the horizontal here, when they collide and they stay the same mass, if they fly apart at the same speed after the collision, then their angles should be identical. And the angle between them should always be 90 degrees. So this is M1, this is M2. This guy's moving this way. If they collide, this was the horizontal. If this one goes off at this angle, then this one goes off at this angle, where we'll let theta plus phi equal 90 degrees. So if theta was 45, then phi would be 45. If this is 60 though, then this is 30. Okay. So that answers one piece. Now, the other part that we have to worry about now is the fact that we have components to deal with. Now, the fact that these two vectors are pointing to both pointing to the right means that there can't be any up and down components. So that means that this component and this component balance out. Well, what are these components? This one's m1, which is just m. And these arrows, by the way, represent the velocities after the collision. So this one was v1, and then this is v1 prime, and this is v2 prime. So this component is the y component of v1 prime. So that is mv1 prime sine of 60. And this is mv2 prime sine of 30. If they're balanced, then these two have to be equal. Again, you don't need the masses. I put the masses in there. I shouldn't have even had to do that because they were already canceled out, so I'm going to get rid of them now. I'm thinking that you could have also shown this to be true for the momentum vectors as well, because remember, the velocity and the momentum vectors have to be pointing in the same direction. So we know what the angles are, but we don't know what v1 prime and v2 prime are. So we have, this turns into one equation with two unknowns. So we do need another equation, and that comes from the x components. What we know is that the two x components here, you have this one and this one. Together, they add up to give us this one. So let's write that out in an equation. So that is v1, which is just x component. This is x direction information. That has to equal the sum of these two x components, which would be v1 prime cosine of theta, which is 60, plus v2 prime cosine of 30. Again, this is, you know what v1 was initially. This is another equation that has two unknowns, v1 prime and v2 prime. So combine that with the fact that you know that in the y direction, I said that these two things equal each other. That's because this statement has to be true in both the x and the y direction. In the x direction, it looks like this. In the y direction, v1 has no y component, so that's 0. And that has to equal a plus v1 prime sine of theta plus a negative v2 prime sine of phi. So that's why we can add this to both sides and essentially set them equal to each other. So you have two equations and two unknowns. You can now solve for v1 prime and v2 prime. Okay. All right, chapter 10 introduces a quantity called power. Power is a scalar. It's just a number. It has no direction associated with it. And there are two ways that you can get power. Power, by the way, has units of watts. Which is also a joule per second. It's how much energy you use, the rate of change over time of the amount of energy. So And when you're talking about electrical appliances, we're talking about electrical energy being used per second. So based on this version of the unit, it makes sense that power is energy over time, or the change in the work done by a system over time. Now, since work can be written in one form as F times delta X, then if we keep F constant, let's say, then I can write it this way. But delta X over delta T is the average velocity. Now, F and V are both vectors, and yet power is still a scalar. When we start talking about vectors in the first couple weeks, you'll learn that this special form of multiplication is called a dot product or a scalar product. And that takes two vectors and turns them into a scalar. So, that should be enough for you to determine, to work on those problems in Chapter 10. And Chapter 11 is dealing with kinetic energy, gravitational potential energy. So, for the most part, those are questions that you should be able to work on your own. So again, let me know if you guys need any additional help via remind or leave a comment below.